Having seen finite automaton and its variants such as non-deterministic finite automaton, deterministic finite automaton, automaton with epsilon moves, we shall look at next something called regular expression. So far we are given a language L, and this language consisting of strings. We say set of all x, and x is over an alphabet, and x satisfies some property p. So this property p could be a pattern like beginning with 1, ending with 0, 0, or contains 0, 1, 1, or equal number of zeros and ones, and things like that. Now, this language, we also saw that a language like this, one can construct a finite automaton. It includes non-deterministic finite automaton, in some cases non-deterministic finite automaton with epsilon. We also saw an equivalent DFA for it. But there are languages for which we may not be able to construct, but so far whatever examples we have seen, for all of them we were able to do this. Now, regular expression is like an algebraic expression using which one can express sets that are accepted by, or languages that are accepted by finite automaton. So regular expressions are algebraic expression, and the objective of this expression, what do they do? This algebraic expression expresses strings present in L, in particular strings that are accepted by finite automaton. Algebraic expression used to represent strings accepted by finite automaton. It could be anything, non-deterministic finite automaton, or with epsilon, or deterministic finite automaton. So given a language or a set of strings, either you construct a finite automaton or you express them using a regular expression, and they are all equivalent. For a given language, you come up with a finite automaton, then one can come up with an equivalent regular expression. For a given language, we find a regular expression, one can find an equivalent finite automaton. This is another way of expressing the set of strings accepted by the automaton. So as the name suggests, it's an algebraic operation, so the algebraic expression, so it will involve operators, right? So it will involve operators, and it's a set of strings, so naturally set theoretic operations will be applicable. So when we say AB, A is a symbol, B is a symbol. AB belongs to sigma. One can also interpret this as A concatenated with B. Concatenation is an operation. In this case, what operation we do? Concatenation. So in general, we are given two strings S1 and S2. They belong to sigma star for some finite alphabet sigma. One can talk about S1, S2, which is S1 concatenated with S2. For example, if sigma is ABC and S1 is AB, and S2 is CC, then S1 concatenated with S2 is ABCC. One can also define S2 concatenated with S1, which means CC followed by AB. So concatenation is one operation. One can also talk about something called A plus B. This means A or B. So this talks about the union operation. You have an alphabet A, you have an alphabet B. One can define A plus B, which says A or B. In general, we have two strings, S1 and S2. One can talk about S1 plus S2, which means S1 or S2, and S1, S2 are strings over sigma. So this one is an operation. On the similar line, one can define something called Kleene closure. This means something like, say, A star. When I write A star, which means it is epsilon A, AA, triple A, and so on. So this says 0 or more A's. When we use this operator A star, this is an operator. So this operator or operation tells you that you can have 0 or more A's. When we write A plus, this is also an operator, which means at least one A. You get A, AA, triple A, and so on. So starting from here, which means 1 or more A's. Now, interestingly, with the operators, so far we have seen 3 operators. One is concatenation. Let me use dot, something like S1 dot S2, S2 dot S1. And another one is OR operator, plus another one is Kleene star operator or closure operator. So we see that with just these 3, one can define sets that are accepted by finite automaton. Languages that are accepted by finite automaton can be described using an algebraic expression involving these 3 operators. And these operators will be operated on some alphabet sigma. And interestingly, this is functionally complete. With this, one can express all languages that are accepted by finite automaton. So let's look at a couple of examples, and as always, try getting some insights out of it and slowly build an invariant, and subsequently we will prove that given an arbitrary regular expression, how do we construct a finite automaton? Given a finite automaton, how do we come up with an equivalent regular expression? So all that we shall discuss next. Note the following. When we write 0 star, which means 0 or more copies of 0, which means epsilon 0, 0, 0, 0, 0, and so on. When we write 0 plus 1, which means 0 or 1. So if you look at the language, then it will either accept 0 or it will accept 1. Now if you say 0 plus 1 star, which means 0 or more copies of 0 plus 1. Correct? So you can see it as 0 copies of this, so which means epsilon, or just 1 copy of 0 plus 1, or 2 copies of 0 plus 1, or 3 copies of 0 plus 1, and so on. In turn, this tells you 0 or 1. This tells you 0 plus 1, this is square, right? So which means 0 plus 1 into 0 plus 1. Now from this I can take 0, from this I can take 0, or from this 0, from this 1, from this 1, from this 0, 1 and 1. So which means when we say 0 plus 1 times 0 plus 1, then you can get 0, 0, 0, 1, 1, 0, 1, 1. So on the similar line, when you write 0 plus 1 cube, which means it is 0 plus 1 concatenated with 0 plus 1 concatenated with another 0 plus 1. Now you will get all possible strings of length 3. You take 0, from this you can get these combinations, so which means 0, 0, 0, 1, 1, 0, 1, 1. Fixing 0 from the first 0 plus 1, from these two one can get 4 possible strings. Or from the first one, let us take 1, and again we get 4 possible strings from the other 2 copies. That shows that we generate all possible strings of length 3. So in general, you get 0 plus 1 k, which means all possible k bit strings over the alphabet 0, 1 can be listed using this. So when we say 0 plus 1 to the power k, what do we get? All k bit binary strings or strings over the alphabet 0, 1. Fine. When we say 0 plus 1 star followed by say 1, 1, 0, which means from this you may get epsilon. So epsilon followed by 1, 1, 0, or it could be 0 plus 1 followed by 1, 1, 0, or it could be 0 plus 1 square followed by 1, 1, 0. So from this is equivalent to saying 1, 1, 0. From this you may take 0 followed by 1, 1, 0, or 1 followed by 1, 1, 0. From this you may get 4 possible strings. With each of them one can combine, one can concatenate 1, 1, 0. So which means 0, 0, 1, 1, 0, or 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1 followed by 1, 1, 0. Now, so this is how things can come when we look at an arbitrary expression. So now that we have understood how clean closure works and concatenation works, OR operator works, let's look at some specific examples. So consider this language consisting of set of x such that x is over 0, 1 star and x ends with 1. So now if you look at the set L, it consists of just 1 followed by 0, 1 or 1, 1, 0, 0, 1, 1, 1, 1, like this. So look at any x, then the prefix is any string over 0, 1. Any string over the alphabet 0, 1 followed by 1. So how do we generate any string over 0, 1? 0 plus 1 star gives you any string over 0, 1. Because you want a string of size say 3. Now if you look at 0 plus 1 cube, you get all possible strings of length 3. Now you want a string of length 7, then you take this 7 times, and now you get to see that all possible strings of length 7 is listed, and the string that we are interested in will be a member of this enumeration. So which means any string over 0, 1 is expressed using this expression. Therefore, the regular expression for this is precisely 0 plus 1 star followed by 1. Now this says if this takes epsilon 1 is 1, and you take just one copy, from that you take 0, then 0 followed by 1, or 1 followed by 1, or take 2 copies of this, in that you take 0, 0 followed by 1. In general, any string over 0, 1 is listed using this expression followed by 1. So the RE for this is precisely 0 plus 1 star 1. Let's look at this language. Set of x such that x is over 0, 1 star, and x contains 1, 1, 0 as a substring. Now any arbitrary x in L has this pattern. Somewhere 1, 1, 0 is present. The prefix of this and suffix of this, it could be any string over 0, 1. Correct? Same is the case over here as well. Which means this part can be generated using 0 plus 1 star followed by 1, 1, 0 followed by another 0 plus 1 star. So this clearly tells you that prefix can be generated using this 0 plus 1 star followed by 1, 1, 0 followed by suffix. You may not find suffix at all. Then in that case take 0 copies of 0 plus 1. You may not find prefix at all. In that case take 0 copies of this 0 plus 1 star. Then followed by 1, 1, 0. 1, 1, 0 must be there. So this comes as it is. So now as you can see, this expression involves OR operator, closure operator, and concatenation operator. This itself 1 concatenated with 1 followed by 0. So 0 plus 1 star is concatenated with the string 1, 1, 0 concatenated with this. Interestingly, just by allowing these 3 operators, one can describe sets that are accepted by finite automaton. So this is an infinite set. The set accepted by this is represented using a succinct expression using operators like plus, star, and dot. Such expressions are called regular expressions. So when we say set of strings, say beginning with 0, 1 and ending with 1, 1, which means it begins with 0, 1 and ends with 1 1. In between it can be any string over 0 comma 1. So we get this. Simplest string that one can think of is 0 1 1 1. In that case, take 0 copies of this. Or 0 1 followed by 0 followed by 1 1. And so this says any string as this property begins with 0 1 and ends with 1 1. In between it can be any string over 0 comma 1. So like this, let's explore a couple of more examples.